Okay, everybody, we're going to be starting chapter 7, which is all about using trig identities and trig expressions to basically, ultimately, I guess our final goal is to be solving equations that use those trig relationships in them, so those ratios in a right triangle. So we're going to be looking today kind of at the baby steps, the beginning of that, where you really have to look at simplifying before you can solve an equation. Think back to pre-algebra, you put together like terms, you did order of operations, and then you kind of worked your way up to being able to solve equations and work with those. So that's exactly what we're going to do in chapter 7. We're going to take these trig relationships, these trig identities or trig functions, and we're going to simplify expressions with them, and we're going to solve equations with them. So we've already looked at their graphs. We've talked about doing just arithmetic things with them. So now it's kind of the natural progression. We're going to take a look at their equations that use them. So before we get into doing anything with that, I just want to talk about what an identity is. And basically all an identity is a statement of equality. So we have an equality between two trig expressions. That's true for all values of the variables. Doesn't matter what the variable is, what that angle measurement is, it's always true. So that's called a trigonometric identity. So think of the word identical. They're exactly the same. So it's a statement of equality. So we're going to be working with those today. Before we get there, though, we have some algebra warm-ups that we really need to deal with. So I'm going to talk these through pretty quickly. If you can, though, if you're kind of watching this for the first time, I'd like you to try them first and then listen to what I have to say about it. I want to see where you're at beforehand. Not that I can actually see your paper because you're watching the video, but I want to make sure that you try this first. So for the first one, I want you to simplify that fraction. The second one, I want you to divide those fractions. And then the third one that you can see right now, I would like you to factor it. If you just want to go ahead and put these on that first slide where it said trig identities, that's fine. So go ahead and pause the video and see if you can do these, and then we'll talk. All right, so for the first one, if you're going to simplify that, what we really need to look at is in order to reduce a fraction or simplify it, it has to be in a factored form so we can divide out a common factor. So the key thing to recognize on this first one is that that numerator is a difference of squares, and it can be factored into two binomial factors, 1 minus y, 1 plus y. We'll do things like this all the time in chapter 7. Now take a look and see what factor it has in common, happens to be a binomial, and I can simplify this fraction by dividing out its common factor. But now be careful. When you divide out a common factor, it leaves a factor of 1 behind. So like 7 divided by 7 is equivalent to 1 over 1 or 1. So when we use the word cancel, it can be really misleading to people. They don't just disappear. It's just not poof, they're gone. They're actually leaving a factor of 1 behind. So just be aware of that when we say that. We'll try to be careful with our language. So what we have left then when we multiply 1 times 1 plus y is 1 plus y. In the denominator, you have 1. And I think most people would agree that probably 1 plus y, that would be the easiest way to say that. So factoring and simplifying are things that we're going to have to do with our trig functions as well. Okay, division. Make sure that you try it before you look at my answer. All right, so process. When you divide fractions, it is the same or equivalent to multiplying by the reciprocal. So I will go ahead and do that. Now let's talk about how we multiply fractions. So using the appropriate language here, we have our numerators and our denominators. So we multiply the numerators together, we multiply the denominators together. So if I multiply the numerators, I would write them as a product. Same thing with the denominators. Now, some people, though, look back and say, hey, wait, can't I simplify before you multiply? And the answer is absolutely you can. If it's easier for you to simplify first and then multiply, great. Or you can do it from what I multiplied together in green. Really doesn't matter. So let's take a look and see what we have in the numerator and denominator that we might be able to reduce. I see factors of x in both the top and the bottom. X to the third over x to the first. I can divide one of those factors of x out, which would leave squared in the numerator and the whole number 1 in the denominator. Do the same kind of thing for y. There's a single factor of y in the top and the bottom, so that would leave 1 in the numerator, y to the first, that is, and a whole number 1 in the denominator. So what we have left when we multiply then would be x to the second times y over 1 times 1 or 1. And again, I would say most people would agree that that would be the easiest way to write it. So we're going to be dividing fractions all the time. Why? These are trigonometric functions. They are trig ratios, we call them. A ratio is a fraction. We're going to use them all the time. Okay, next one, I wanted you to factor this one. So make sure that you check and see what that means here first before we keep going. So we're going to factor. First thing you look for when you factor, greatest common factor, which in this case is the x, and then that would leave behind 1 minus y squared. So this concept of factoring, oops, gosh, put it in the wrong place. This concept of factoring is really going to be critical to what we're going to do as well. So it's one of those things that we can do to try to rewrite things. Now, look inside. Is there anything you can do more? Well, that's that difference of squares again. So I can rewrite that difference of squares as a product of two factors, binomials, 1 minus y, 1 plus y. That's the idea of factoring completely, so we want to make sure we go as far as we can. Okay, here's your last one that I want you to do, and I want you to just to do the operation of addition. I want you to add those two together, so we want to add those. Now I'm going to give you a moment, make sure you pause the video, see if you can do this, and then we'll talk. Okay, so first thing, have to have a common denominator if you add or subtract. Right now it's not common, so I need to look at the factors I need to make both denominators to make it a common denominator. Just like if you had something over 5 and you have something over 7 and you want a common denominator, you need both the 5 and the 7. 5 times 7 would be your common denominator. 35. We need to do the same sort of thing here to make sure we have what we need. So I'm going to need the x minus 3 and the x to be in my common denominator. So I need both of those. So what do I need in this first fraction then? Well, I have the x minus 3. I'm going to need to multiply top and bottom. Has to be equivalent to 1, right? We're changing how the fraction looks, not its value. So x over x equivalent to 1. So multiply, that would be x. I'm going to leave this just as x times x minus 3 right now. I think it's easier to be able to simplify it later if you don't multiply it out right away. But you could. The second fraction, I'm going to multiply top and bottom by the other factor, so x minus 3, and that would give us 3x minus 9, just distributing up top on the numerator, and then x times x minus 3. Okay, in Algebra 1, kids are usually exhausted by this point, like, oh my goodness, this is so much work, but you haven't actually done the operation yet. Remember, you're supposed to be adding. So next order of business, now that you have a common denominator, is add. If you have like terms in the numerator, put them together. So 1x plus 3x. In the denominator, we're trying to see how many of these x minus 3's we have. So that's our denominator. Now, what I would do is take a look and see if you can simplify that fraction at all. Look up top in the numerator. Can you factor 4x minus 9 at all, this binomial? Any GCF? Nope. Can I do it in binomials? Nope. So that means it is in its factored reduced form already. So 4x minus 9 is as much as I can do. Do you see that factor in the denominator? In other words, could I divide anything out? Well, no, they're not the same linear factors. So all you can do is just either leave it the way you had it, or you can distribute in the bottom if you like that better, and that would be fine as well. Some people like that to be able to see what they have for that rational equation. So we can talk about asymptotes. You can do whatever you needed to do. Now, adding and subtracting is a big part of what we're going to do too, so we need to be able to do that with fractions. Okay, so now let's switch gears back to trig. So transitioning now back to trig world. So that's algebra. You're going to use all of those skills. So before we can start doing the fun stuff with this, not that identities aren't fun, but to actually get to simplifying and working with expressions, we have to know what expressions we can be working with. So we have these identities, these things that are always true that we can use. So the pink sheet that you have that has all of these on there, you want to kind of reference that too. You will find all of these on there. The first group is called reciprocal identities, and we know what reciprocal is, 1 over. So the reciprocal identities are the building blocks that we've been using for a long time. So sine, its reciprocal is cosecant, so the sine of theta would be 1 over cosecant of theta. You could do it the other way. Cosecant's reciprocal is sine, so that would be cosecant equals 1 over sine of theta. So those are called reciprocal identities because that's how they're defined. It's just the reciprocal. Notice I wrote theta after each of them. You could never just write sine with nothing after it. It has to be sine of an angle. Otherwise, there's no triangle, there's no ratio involved. So always sine of an angle. All right, cosine's reciprocal is called secant, so that would be 1 over secant. So then secant could be 1 over cosine of theta. And then tangent's reciprocal is cotangent. Whoops. Going to write the same thing twice there. 1 over cotangent, and then cotangent's reciprocal is 1 over tangent. So when we look at those relationships, those are all reciprocals, and they come in really handy. All right, the next ones are called quotient identities. What's a quotient? Think about back to your basic operations. Which operation is quotient? Division, right? Okay, so these are all coming from something being divided. So let's look at the first one, sine divided by cosine. Think back to our pictures. Sine, when we think about our unit circle, sine is the y value, right? And cosine is the x. So which trig ratio is y over x? Or that other mathematical concept we've talked about before, slope? Which one is it? Tangent of theta. If you came up with that one, give yourself a pat on the back. Good job. So tangent of theta, that is sine divided by cosine. It's a quotient identity. We're going to use it all the time. So let's see if you can figure out what the other quotient identity would be. Cosine over sine is the reciprocal of the one that we just did. So what's the reciprocal of tangent? That would be cotangent of theta. So those are called quotient identities. They're very handy. Okay, the next ones we're going to do to kind of finish up with our identity piece before we get to our examples is the Pythagorean identities. You guys know Pythagoras. Well, not personally, because, yeah, he died a long time ago, Greek mathematician. But if you knew him, you could have talked to him about a really cool thing that he came up with about right triangles. Do you remember what I'm talking about? Oh, the Pythagorean theorem. Yeah, so let's see if we can draw a picture where the Pythagorean theorem might be helpful. So we're going to go ahead back to this wonderful unit circle drawing that we've done like 1,000 times here. Well, that's an exaggeration, but you know what I mean. We're going to put in an angle theta in standard position. That means vertex at the origin, initial ray on the x-axis, terminal ray somewhere, and that terminal ray intersects the circle at a point. So that point, we called it P. It has coordinates in the coordinate system. It would be an X and a Y to get there, and we have our point. All right, now where did the triangle come from? Well, we dropped a perpendicular down to the x-axis, and we get our nice little right triangle here. So the horizontal component of that triangle would be however far we moved in the horizontal direction, which would be your X. The height of that triangle would be how far we move vertically, which would be y. And if it's a unit circle, the hypotenuse would be 1. So I want you to use Pythagorean theorem on this triangle. So Pythagorean theorem says the one leg squared, so x squared, plus the other leg squared equals the hypotenuse squared. So x squared plus y squared equals 1. Now, I know a lot of people memorize it, a squared plus b squared equals c squared. Well, what if it isn't labeled? Or what if it's not a, b, and c? So think of it leg squared plus leg squared equals hypotenuse squared. A lot easier way to think of that. Okay, now let's change over to our trig language then. So I want you to do the cosine ratio for theta in that triangle. Cosine would be adjacent over hypotenuse, so x over 1 or just x. So if you remember way back when here when we first did our unit circle, cosine of theta is x. That's what it's equivalent to. Okay, well, same idea. Then I want you to think of the sine ratio in that triangle. Sine would be opposite over hypotenuse, so y over 1. So sine is y. So sine of theta is y. So I'm going to replace and rewrite this Pythagorean theorem sentence now, this one right here, but I'm going to replace cosine with x and sine with y. Now I'm just going to have you listen to it and see what you write down. I want you to write cosine squared of theta, or the value of cosine of theta squared. Now, a lot of people run into trouble because some people write this. Now, the problem with that is it looks like what's being squared? The angle, not the function itself. So we have to be careful. So some people fix that by doing this, which is great, and that works fine. And some people write it that way. It just gets to be a lot of writing. So kind of common convention has become this. Write the function first, square the function name, and then the angle measurement. So you're not actually squaring the angle, you're squaring the function. So cosine squared plus sine squared is equal to 1. So if we just use our Pythagorean relationship, that's what we get, which is the one that you see up at the top of the slide here. So sine squared plus cosine squared equals 1. Now, if you look at your pink sheet, though, you have two other versions of it, and I want you to see if you can figure out where those are coming from. If I take this initial expression that I just had and I solve it for, say, cosine squared and subtract sine squared on each side, I would get an expression that looks like this: 1 minus sine squared of theta. Or I could have done that for sine squared as well, right? So sine squared equals 1 minus cosine squared. Those are two other versions that are saying exactly the same thing. So all three of those, they're all identities that are representing the same set of values, the same numbers. Just depending on what we're doing, we might prefer one over the other. So realize that if you look at your pink sheet, they're all there. Okay, so the other two Pythagorean identities that I want to talk about, we're not going to go through the proof of these, but let's look at this one. Tangent squared of theta plus 1 equals secant secant squared. See if you can find that one on your pink sheet. If you notice, there are two other versions of that one on your pink sheet. If you solve this for tangent squared, in other words, subtract 1 on both sides, you would get this. And instead, this original one, instead of solving for tangent squared, what if you got the 1 by itself? Then that would be secant squared minus tangent squared. So those are just 3 different versions of basically saying the same thing. So all 3 of these are the same identity, just written with terms on one side or the other. All right, so our last one, Pythagorean identity, and again, I'm not proving these, but they all come from right triangles. We can do the same thing with. So that original one, what if I solved it for cotangent squared instead? So I can move the 1 over, subtract the 1, or I could get the 1 by itself and move the cotangent squared over. So there's 3 different versions of writing that one as well. So this is kind of a what am I using it for down the line, which one makes the most sense for doing it. Okay, so we've talked about our skills long enough. We need to jump into this and actually do some problems. So for our first day here, we're just going to start with some basic ones, and then we'll kind of ramp up the coolness factor as we go through them. All right, so let's take a look at the first one. So I see cosine squared of x times tangent squared of x plus cosine squared of x. And the directions are this wonderful word simplify. So I want to talk about what does that word mean first. When you in algebra or on the ACT or wherever you're looking see the direction simplify, I want you to think about what kinds of things you might want to do if it says that. Okay, so see if you can think of any. So oftentimes some of the things that pop up in the list are like add, because I see an addition there, or multiply, or do operations, like do order of operations. And I'll say order of, I guess. So we want to make sure we do it in the right order as well. So do order of operations, but do the operations, right? Or some people might say like terms. See if you can put things together. I would say that's kind of like doing operations, right? 2x plus 3x, that kind of thing. Putting things together, doing operations. Think about what we did in our warm-up, some of the things we did. We did some operations, but our first example was factoring, right? Being able to put things together or pull things, separate them out so we can simplify or whatever it might be. So maybe it's factoring or maybe it's going the other way. Maybe it's distributing, which I know a lot of people remember if it's binomials, they call that FOIL. I would argue that kind of goes back to doing operations, but distribute, sometimes people think almost separately because it's maybe a step to get you started to do something. So do the operations, see if you can put things together, try to factor it, try to multiply, whatever you can do to try to make it easier. And what we mean by easier is the fewest operations and the fewest functions, so we can get it down into something that's a little bit more manageable. Okay, so I want you to take a look, grapple a little bit, see if you can go down that list and find anything that would work. And then pause the video, see if you can try some things, and then kind of start back up. This is one of these places where the struggle and the trying things that sometimes it works, sometimes it doesn't, you got to try something else, is fantastic because there's lots of different ways that these can be done. There's lots of different avenues and ways to think. And for some people, that's really liberating, really exciting because you can do it lots of different ways. And some people just want one way that works, but there are a lot of different methods. So take a look and see what you can find. Go down the list. Okay, so when you talk about do operations, I can't add those together. They're not like terms. One has a tangent squared with it, the other doesn't. So I'm really kind of stuck there. So I can't do any of the operations, and I don't have any like terms. So the next thing on my list is factor. So let's see if there's a way that I can do that. So it looks like there's a cosine squared in each one of those terms. So I'm going to pull out the cosine squared, and that's going to leave tangent squared plus 1, tangent squared of x plus 1. All right, so now here's where we're going to have to kind of deviate a little bit from our previous list. I still can't do any of those operations, but what I want you to do is look back inside here and look back at our identities. And I want to see if you see anywhere where it says tangent squared plus 1. If you look right at the top here, I see a tangent squared plus 1, and what is it equivalent to? Secant squared. So what I'm going to have you add to your list here, and this is something that we don't normally think of so much in algebra, but substitute. There's going to be ways that we can rewrite things in trig because of these identities. So I can replace or substitute that entire expression tangent squared of x plus 1 with secant squared of x, and I've just made that a little bit easier to deal with. So I have now only one operation left. I only see multiplication and only those two functions. Okay, so now I want you to take a peek again and see I can't actually multiply those together. So think if we can use this again. Is there a way I can substitute again to make this better? So go back to your identities and see if we can come up with anything. All right, so here's a question for you. What do you know about cosine and secant? These two functions, cosine and secant. They are reciprocals, right? Looking right in the middle here. So cosine is 1 over secant. So if we have a cosine squared, that would be 1 over secant squared. Totally fine to do that. It's a ratio squared. Or secant is 1 over cosine. That means secant squared is 1 over cosine squared. It doesn't make any difference. You can use it either way. I think I'm going to change over the secant squared one into 1 over cosine squared. And now I can go a little bit further, right? So now I have a multiplication, but everything is in the same function. They're kind of like terms now, right? I can put things together a little bit easier. So you can either multiply it first, which is totally fine, or you could have reduced, simplified first. Cosine squared divided by cosine squared is 1. We've simplified it all the way down to there. So kind of boxing the final result, but it's the process that matters. How did we get there? So just look back at that red step. Cosine squared times secant squared. What happens when you multiply a function times its reciprocal? Well, you always get 1, right? So some people can see that right away. So factoring is a great strategy for this one. All right, so hopefully you have everything you need. I'm going to erase this. What if we hadn't seen the factoring? I want to show you another option that works really well too, and it goes back to this substituting. Sometimes you don't know where to start and you're just going to get stuck. One really good strategy in our toolbox is to change or substitute everything. So every expression that you have, so every trig ratio that you or function that you have, into sine and cosine. So the function sine and the function cosine, and then do the operation. Sometimes it's easier to put things together if everything are in the same function. So we're going to change everything into sine and cosine and see if we can do any more with that. So let's try that method on this one. So cosine squared, I would probably just leave that. It's already cosine. Tangent squared, you have a couple options, but if you're looking at the sine and cosine version, that would be down here in this quotient one. So tangent is equal to sine over cosine. So tangent squared would be sine squared over cosine squared. All right, now the last one again. It's already in cosine, so I guess I would just leave it. Everything might be a nice idea to write everything as a fraction. People lose their numerators and denominators here, so be careful. Don't lose your numerator or your denominator. It's not good to lose your top or your bottom, right? All right, so let's see what we can do. I see a multiplication and I see an addition now. So I see a times here and an add. So let's see if we can just do those operations. So follow order of operations, see what happens. When you multiply the first two fractions together, I can simplify those cosine squares. They divide out and leave a factor of 1. It's just like having a 4 over 4. They're the same expression. So what does that leave me with? Well, 1 times sine squared is sine squared over 1 plus cosine squared over 1. Don't really need to think of them over 1 now, I guess. Some people wouldn't even write that. Sine squared plus cosine squared. That's what we're trying to simplify now. Well, gosh, that sounds familiar. Look back at your pink sheet or your notes here. Sine squared plus cosine squared. Oh, look, up at the top. Sine squared plus cosine squared is what? 1. Sure, we knew what this one was supposed to be, right? We had already done it one version, but we could do it this way as well. So kind of that wholesale substitution, everything into sines and cosines, oftentimes will allow you to do some operations. Not always, or maybe that's not the easiest way, but it's a way, and it gets you to that result that we need. All right, so we're just going to do a couple more here to kind of finish this off. Really important things that we're talking about here today. So let's take a look at the first one. Thinking about what we just did, I can't actually divide those. So let's see if there's substitutions I can make. So for tangent, I'm going to substitute sine of x over cosine of x. Sine of x is already in sine, so I don't need to worry about that. So everything's in sine and cosine, and it's an operation that I know how to do. It's division. So to divide fractions, I'm going to multiply by the reciprocal. And when I multiply by the reciprocal, if I can simplify that fraction, fantastic. So when I divide out my common factor of sine, it leaves behind a factor of 1 in the top and the bottom. So important. People often mistake this one. It's 1 over cosine of x that we have left now when we multiply. Don't lose your 1. That factor, when we divide it out, leaves a factor of 1, 1 over 1. Now, is that enough? Is 1 over cosine simplified, do you think? So if you go back and look at your list of possibilities, is there something that you could replace 1 over cosine with? Well, it looks like it's secant. So the question is, do you think that's a better answer? Well, I think a lot of people would say it is because now you no longer have a division. It's just a single function name. So if you can get it all the way down to a single function, that's fantastic. Okay, now I want you to take a look at the one on the other side here. I would probably start with a very similar strategy because there's not like terms here. Tangent and secant are different and we can't multiply them. So I'm going to go ahead and replace tangent and cosecant. It's a reciprocal for sine. And I end up getting a very similar thing happening. I can divide out my factor of sine. It leaves me with a 1 over cosine. And again, that is a secant. So interestingly enough, these two have the same answer. And I want you to look back at the original function and see if you can figure out why. Dividing by tangent is exactly the same thing as multiplying, or dividing tangent by sine, I should say, is exactly the same thing as multiplying by cosecant, right? 1 over sine is cosecant. That means this relationship up here is an identity. It is always true. They are the same value. So there's so many of these that we're going to run across. When we simplify things, we create new identities to look at. Okay, we're going to finish up this part 1 with this last example, kind of working with that same strategy. I see subtraction and multiplication. There are no like terms. I have 3 different function names. So really, I can't do those operations. There's no GCF the way it's written, so I can't factor it either. You are really stuck with just change things over. So I'm going to go ahead and do that. So I'm going to write everything into sine and cosine. The things that are already sine and cosine, just leave them. Cotangent is cosine over sine. All right, now, order of operations, I see a subtract and a multiply. So I'm going to go ahead and multiply. So cosine times cosine. Just like x times x, that would be cosine squared of x, and then 1 times sine is sine of x. All right, now subtraction. When you subtract, you remember you have to have a common denominator, but excellent. There happens to be a common denominator, which is fantastic, but the numerator doesn't have any like terms. No problem. I'm just going to go ahead and write that as a statement. Put them together in the same numerator, but I know I can't combine them as a like term. All right, now a lot of people always are asking the question, okay, how do I know if I'm done? Is this simplified enough? Okay, well, if there's any substitutions you can do to make it better, you should. So I'm going to have you go back to the Pythagorean identity page, and I want you to find down there wherever we said 1 minus cosine squared. So 1 minus cosine squared right down here is equivalent to sine squared. So can that help you here? Well, 1 minus cosine squared, if I replace that with sine squared of x, now everything in my ratio is in terms of sine. It's just like having a y squared divided by a y, like we did in our warm-up question. You can actually divide one of those sine of x's out, which would leave you with sine of x. Fantastic. So if you can make a substitution that makes it better, then absolutely do that. And what do I mean by make it better? Fewer functions, fewer operations. So see if you can do that. So our day 1, we're just going to practice those basic questions like that. Day 2, we're going to do a couple more examples and kind of lead into some more even exciting situations that you might run into.